Hello everyone, I'm Hyangsuk Min. Today's seminar will be a paper review. The paper I will be presenting is titled FIZZ Factual Inconsistency Detection by Zoom in Summary and Zoom Out document, which was published at 2024 EMNLP. This paper focuses on improving NLI-based evaluators, which is one of the methods used to assess the faithfulness of large language model summaries. Before diving into the paper, I would like to briefly introduce NLI-based evaluation. NLI-based evaluation follows this process. We set the original text as the premise and the generated text or a summary as the hypothesis. Then evaluate the relationship between these two sentences by selecting one of three labels: entailment, contradiction, or neutral. Entailment measures whether the premise contains or implies the hypothesis. Contradiction measures how much the hypothesis opposes the premise. And neutral measures the logical relationship between the premise and hypothesis. The higher the entailment score, the more we can judge that the hypothesis maintains a factual consistency with the premise. The paper we're discussing today has four key motivations. First, when evaluating summaries at the sentence level, it's difficult to identify the various facts contained within each sentence. Second, when a summary sentence contains multiple pieces of information, it's challenging to pinpoint which specific information is incorrect. Looking at the sentence in the red box in this example, if we evaluate the factuality of the entire sentence as a whole, we can only tell that something is wrong with the sentence, but we cannot identify which specific part is incorrect. That's why in this paper, they break down its summary into atomic facts for evaluation. By evaluating these atomic facts separately, we can identify exactly which facts are problematic. The third issue is that when pronouns appears in either the summary or the original document, evaluating at the sentence level can lead to incorrect assessments. For example, as shown in B, when we have a sentence like he added, it would be a massive something. And compare with it atomic facts, we cannot verify if he is Gunter, resulting in a low score. As shown in C, if we replace the pronouns he with Gunter before evaluation, we can properly assess the factual relationship and achieve a higher score. Additionally, when evaluating at the sentence level, we can't properly assess atomic facts that contain information from multiple sentences. For example, in A, if we compare the two sentences separately, we can't properly evaluate the factual information contained in the atomic facts. However, as shown in C, combining these sentences allows for proper evaluation. Based on the motivation that I just explained, here are the main contributions of this paper. They introduced a new system called the FIZZ, which improves the accuracy of summary factuality evaluation and provides better interpretability. They enhance the factual consistency evaluation by converting pronouns into explicit named entities. Third, they enable more detailed summary evaluation by breaking down summary sentences into smaller atomic facts. Fourth, they propose an adaptive granularity expansion methodology for summaries that require reasoning across multiple sentences. Now let's move on to the methodology. Here is the overall architecture of FIZZ. And FIZZ consists of 5 stages. First, they convert pronouns in both the summary and the original document into explicit entities. Second, they break down the summary into the atomic facts. Third, they perform filtering since the decomposed atomic facts might contain factual information different from the summary. Fourth, they calculate pairwise factuality scores between the original document and the filtered atomic facts, generating a score for each atomic fact. Finally, since some atomic facts require comparison across multiple sentences rather than just single sentence, they apply granularity expansion to recalculate these scores. And the final factuality score for the summary is determined by the lowest score among all the atomic facts. First, let me explain atomic facts decomposition. Before atomic facts decomposition, we perform coreference resolution to address these issues and factuality checking caused by pronouns in both the original document and the summary. Through this coreference resolution, we convert the original document D and summary S into D' and S', respectively. Atomic fact generation is performed on the summary S', creating A' for its sentences S' in the summary. The paper defines atomic facts as follows. They are short and concise sentences that contain at most 2 or 3 entities. We person entities specifically using explicit name entities rather than pronouns. They use an LLM to generate these atomic facts. By breaking down summary sentences in 2 or 3 atomic facts, they decompose the summary into multiple sentences, each containing a single piece of information. This process enhances interpretability by allowing us to identify errors in the summary sentences in a more detailed way. Here is the prompt used for LLM. When using an LLM to generate atomic facts, sometimes it can generate sentences containing information not present in the original text. To address this issue, they utilized an EMNLP-based methodology. The EMNLP-based approach provides probability values for entailment, contradiction, and neutral relationships. They set the summary S' as the premise and the A' as the hypothesis. Based on the EMNLP evaluation, they keep the atomic fact only if the relationship between the two sentences is classified as entailment, otherwise they remove them. Through the previous steps, we've generated atomic facts and filtered out all but the most relevant ones. In the next step, we calculate the factuality score between these atomic facts and the original document to determine the overall factuality score of the summary. First, we calculate scores through fact-checking between atomic facts and the original document. We generate pairs between every sentence in the document and every atomic fact to calculate individual scores. The score calculation process is the same as what I explained in the filtering stage. We set each document sentence as the premise and atomic facts as the hypothesis to calculate probability values for entailment, contradiction, and neutral relationship using an EMNLP-based evaluation. Among these, we use the entailment probability as atomic fact score. Since each atomic fact is scored against all sentences, we select the highest score as the final score. These create a score vector T containing atomic fact scores for the summary. Using single-sentence comparison as described before, some atomic facts end up with low scores. This happens because it's difficult to understand the factual relationships contained in atomic facts when using just a single sentence. To serve this, instead of using single sentence, they use multiple sentence, which is an adaptive granularity expansion. They recalculate the atomic fact scores by incorporating both previous and next sentences. They don't recalculate scores for all atomic facts, only for those with notably low score. For atomic fact A prime K, we typically use the entailment value as its score. However, some atomic facts might have higher values for contradiction or neutral than for entailment. They determine that these atomic facts are difficult to fact-check with single sentences, so they only recalculate scores for these cases. Through this process, scores for some atomic facts are recalculated and replaced, resulting in new T-star. Finally, the overall factuality score for the summary becomes the lowest value in T-star. Here is the pseudocode for adaptive granularity expansion. They firstly do atomic fact scoring for all document sentences and find out the document sentences that has maximum score. And then they check does the score is the maximum among entailment, contradiction, and neutral. If not, they proceed to adaptive granularity expansion. And here is the overall process for adaptive granularity expansion. Now let's move on to the experiments. Here are the experimental settings. First, they use MT5, a sequence-to-sequence based model for coreference resolution. For atomic fact composition, they use Orca2, which is Microsoft's fine-tuned version of Llama 2. For NLI, they use SUMEC. For benchmark dataset, they use AgriFact and ROSE. AgriFact was used for faithfulness evaluation, while ROSE was used to analyze atomic fact generation performance. They used balanced accuracy as the faithfulness evaluation metrics. The baselines are divided into 4 categories: QA-based, parsing-based, NLI-based, and LLM-based. Now let's look at the result of the faithfulness evaluation. FIZZ demonstrates higher performance on average across both CNN and Axum datasets from AgriFact. Through the ablation studies below, they prove the necessity of each component, granularity expansion, for atomic fact filtering, and atomic fact generation. Next, they show that FIZZ consistently have better performance across all datasets compared to other methodologies. It achieved higher performance than LLM-based approaches like FactScore and FactTool. And they also conducted 3 types of analysis. First, they analyzed how different LLMs affect atomic fact decomposition and the resulting performance changes. They compared 5 different LLMs: JAPA, GPT 3.5 Turbo, and GPT 3.5 Turbo Instruct, Mistral, and Orca2. And Orca2 showed the best performance among them. This is because generating shorter atomic fact leads to better performance. as each atomic fact contains only one piece of information. Next, they analyzed how similar the atomic facts generated by different LLMs were to human-generated atomic facts. While the 53.5 Turbo generated atomic facts that were most similar to human-generated ones in terms of context, it showed lower performance due to generating longer atomic facts. In conclusion, generating atomic facts with appropriate length and quantity has a significant impact on faithfulness evaluation. Next, they analyzed the scope of granularity expansion. For CNN, performance improved when using up to 3 sentences, while XM, performance continued to improve as the number of sentences increased. XM shows better performance with more sentences compared to CNN because it has a strong tendency toward abstractive summarization. This demonstrates that granularity expansion methodology has a significant impact on faithfulness evaluation performance. Finally, they analyzed the performance of coreference resolution. For the CNN dataset, they observed significant performance improvements when applying coreference resolution to both the summary and the original document. In contrast, XM showed the highest performance when coreference resolution was applied only to the document. They attribute this to XM's summaries having a higher tendency toward abstractiveness, which limits the performance improvement from coreference resolution. At the last, the paper points out the limitation of their methodology. At the last, the paper points out the limitations of their methodology. They acknowledge that in appropriate atomic facts, decomposition can sometimes result in lower faithfulness scores compared to sentence-level evaluation. In conclusion, a novel method of FIZZ is proposed, which decomposes the summaries into atomic facts and conducts a sentence-wise comparison with the document in detecting summary factual inconsistency. Second, the proposed system has higher interpretability due to its ability to precisely identify which parts of a summary are factually inaccurate by breaking it down into atomic facts. Third, the paper analyzed the necessity and significance of coreference resolution and granularity expansion in the context of summary factual consistency checking. Thank you for listening to the presentation.